From our knowledge of SN2 reactions, we already know that alcohols react with hydrogen halides to produce alkyl halides. And so if we start with an alcohol and expose it to HX, the first step will be protonation, which will then generate a good leaving group of H2O+. And upon displacement, we'll get Rx and H2O. In our Rx, we'll be susceptible to a whole range of SN2 reactions. So this is another way of converting alcohols into electrophilic reagents that can be displaced through nucleophilic reactions with nucleophiles. For example, with HBr and a tertiary substrate, this reaction will actually work quite well without any assistance, because we'll get stable tertiary cation, which will then react with Br- to give us a T-butyl bromide. And this will be SN1 reaction, which occurs with tertiary substrates. The other extreme would be SN2 reaction with primary substrates. And this will, upon protonation by HBr, generate protonated alcohol, which again is displaced, but now in a concerted fashion by Br- to give us this butyl bromide in an SN2 reaction. With HBr, these things work quite well. With HCl, things get to be a little slower because Cl- is a worse nucleophile. Than Br-. Okay? And so with tertiary substrate, it still doesn't matter too much, because even a weak nucleophile will be able to displace H2O plus group since we form a cation anyway. But with secondary, and especially with primary substrates, HO groups needs to be activated, and one of the most common ways of activation is to use zinc chloride. The zinc chloride is a Lewis acid which will coordinate to oxygen, giving us positive charge here and negative charge here. And now this is much more easily displaced by chlorine. In a reaction we generate butyl chloride and this zinc species. Okay. Now SN2 reaction with zinc chloride is still pretty slow, but it's significantly facilitated versus the reaction without any added zinc chloride. Secondary substrates, when activated with zinc chloride, go into a quick SN1 reaction, so this is a way to speed things up. And so if you look at this carefully, you realize that even though this is in principle useful, there are quite a few problems with direct reaction of alcohol with HX, because the first problem that we encounter are eliminations. And eliminations come about that if we get a strong acid and an alcohol, we generate a good leaving group and then a cation, or we generate conditions that are acceptable for eliminations. The second problem comes from rearrangements. This occurs mostly in secondary and tertiary substrates, which can form cations, but if these cations are not the most stable species that can be formed under given conditions, they will rearrange and give us undesired products. The third problem comes from the poor yields of primary and secondary substrate with HCl. We've seen that even with zinc chloride activation, primary substrates don't react too well, secondary kind of do react, but not too much. And then finally, the final problem is that this simply doesn't work too well with HI. And so getting alkyl iodides is difficult using this method. At this point we will finish today's lecture, and next time we will see how to overcome these problems and generate under reproducible conditions various alkyl halides. But to sum up today's lecture, we've seen a handful of reactions of alcohol. We started with their oxidation, both in lab and in biological conditions, and then we went to the reduction through sulfonate esters. And sulfonate esters are good species derived from alcohol since they have a good leaving group, and they can be displaced by a variety of reagents. In terms of reduction, we displaced them with H- to get an alkane from an alcohol. And finally, we finished with reactions of alcohol with HX, which mechanistically should work quite well, but they encounter quite a few practical difficulties, which we'll see how we overcome in the next lecture. Thank you.